thief who stole my glasses, I will find you. I have contacts. Because contacts let you see, but also help have connections. Explain the joke always makes it funny. All right. Hello, everyone. Welcome to the half of us that are here on time. 3. What would you all say? 50%, 60%? Yeah, we'll say 60%. This will get worse and worse as the year goes on. But I, love seeing y'all. So, as always, logistics updates. Our exam. So I'll actually send an announcement about this because we're at that point where I need to start giving y'all details. There, look, here's us for that blue dot on the 17th. And there's the exam on the 26th. The first midterm exam, test, whatever word you want to call it. Basically our first assessment, major assessment. So, reminder to you all, what is on, how do you prepare for this, what's on this, all that jazz. Problem set 1. Everything from problem set 1 is free game. Everything from problem set 1 is free game. So, as I've said many times, if you haven't looked at it yet, do so because we're running out of time. So, problem set 1 is free game. And then the other thing that's free game is the clicker questions that I give you all in class. Clicker questions are also free game. So, basically, the breakdown of the test will be 20 multiple choice questions, and then there will be 3 free response questions, but you will only pick 2 of those. 3 free response, but you will only pick 2. No matter which 2 you pick, the major concepts on this test, you can see it in this list, kinematics and forces. That's the bread and butter of this test, kinematics and forces. So no matter which 2 free response you pick, you'll be assessed. You'll be doing both things. But I give you a choice because I think it's nice. It's all physics. At the end of the day, I'm testing whether you know physics. And I think one of the things that can really stink is if you see a problem, sometimes certain problems can wake people up. So it gives you a little bit more flexibility and a structure that is generally not flexible. So for the 20 multiple choice, the way it's going to work is about 60% of those will be numerical plugging in things. 60, maybe 70, somewhere in that range. 60 to 70% will be actually doing math. The other 30 to 40% will be like conceptual questions. It'll be our quicker questions. That's kind of the breakdown. 60 to 70% of the multiple choice will be like actually doing math, like the problem set problems. The other 30 to 40% are like our clicker problems. That does not necessarily mean that the clicker problems, if you know what you're doing, are very quick because there's no math involved. That does not necessarily mean they're easier. Remember, I told you all last time that for some people, the numerical problem solving is often much easier and the concepts are trickier. So I say all that. Just make certain you scroll through the PowerPoints and kind of look through the questions that I've asked. Make certain you can answer those and you know how to solve, why the answer is what it is, all that jazz. There's some concepts we've talked about throughout those, and that's how I ask those questions. So, and the reason for that is time-wise. So we are also blessed. Time will not be a concern in here. Time will not be a concern. I am designing this test for 2 hours, maybe even only an hour, 40 minutes, actually. You will have the full 2 hours and 50 minutes. One of the beautiful things with Studio is we have a ton of time. So time will not be a concern. Granted, if you have accommodations through SAS, please do make use of them. I do encourage you. If you have that extra test time and stuff like that, you have to submit those requests, I think, a week in advance of the test. So it never hurts to do that. You lose nothing by doing that. But in general, one of the beautiful things with Studio is I actually get to give you all way more time than you all need for this test. And the benefit of that is you should very much check your work. Don't second guess necessarily the logic you followed, but definitely double check your math. Definitely double check your math. Double check if you used cosine or sine correctly, things like that. Whether you put G as negative 9.8. Don't necessarily double check your process. More so double check that you broke things into components correctly or things like that. I can almost guarantee you if you double check your work, you'll find a mistake because you're a human and there's 20 questions. And if you think you have like a 5% error rate, then that's one question out of 20. Like, depending on what error rate you assign to yourself. That's my recommendation. It is not fun to do to check your work because at the end of the test, you probably want nothing more than to just turn it in and move on with your life. But you will learn at some point in your, like, it took me to the end of my undergrad to realize this. When I started checking my work, I almost always found a mistake somewhere. Almost always. That was my experience. Again, mileage may vary, but be prepared for that. So that's just one of those pro tips. You can learn it for yourself, or you can learn it now. Test it, see if I'm right or not. All it costs you is some time. And it's a good practice to get into when you get into industry and stuff like that. Double check your work because a grade is like the least consequence you can have in life. People's lives, money, all that kind of jazz. All right, so we are in Newton's laws, and we are basically going to be just doing problems. There is a few extra concepts. Yeah. Oh, you missed it. It was for those who lost. Whoever stole my glasses, I'm going to find you. I have contacts. Yeah. That's a good one. They're always good. They're all good. I'm not about this. Totally. So there's basically a few main chunks left. We got to learn how to do, like we're going to practice some free body diagram problems, some force problems. At some point, we'll get to inclined planes. We'll talk about friction. That's a major concept we need to know. We're going to do a pulley problem at some point, and then we'll get into centripetal force. But it's all forces. It's all forces. The name of the game is free body diagram. Sum up your forces in the x and y, and the sum of your forces equals ma. That's the recipe again and again and again and again and again. Now, this problem, the one we're going to work on, I like this problem for a couple reasons. One, it's it's easy to visualize. When we talk about force problems, there's something very important. And it's where do you focus on? What part of the picture do you draw a free body diagram of? So I've mentioned this in the past. If you drew a free body diagram of the entire universe, it sounds silly, but it's really easy to do. Here's the universe. Remember, everything looks the same. Newton's third law says for every force, there's an equal and opposite. And so the free body diagram of the universe looks like this. The net force is 0. If you look at an entire system, it's very often that all the forces will cancel out. If we look at you in your chair right now, so you in your chair, and this is a complete aside, but this is a really important thing. Where you zoom in on the picture matters. Where you zoom in on the picture, what you are referencing matters. So let's, really quick, here's you on a chair and all your chair goodness. There it is. Looks just like you, right? All right. If you look at you, this is the free body diagram for a person. Gravity pulls you down. Normal force pushes you up. That's the free body diagram of you. If you look at the chair has its own free body diagram. See if y'all can draw a free body diagram of all the forces acting on the chair. Try it out. See if you all can draw. I drew it for the person. We've already seen that in the past. I want to see if you all can draw the free body diagram of the chair. All the forces acting on the chair. Depending on where you look, you get different forces. And that's an important concept. We're going to see that today again and again. Which way is that? Yeah. As a checkpoint, if you only drew 2 arrows, you didn't draw any. You did not draw enough arrows. Okay, so you go down on the force side. Which way does the one from the person point? So the one from the person points down, gravity points, and then from the. All right. So the result of this is the person pushes the chair down. So you could call that all sorts of things. I heard people call it the applied force. I heard people call it the normal force to the person. It really doesn't matter. Call it whatever you want. I can just call this the force of the person if I even wanted to. Force of person, force applied, force normal. Doesn't matter as long as you know what it is. Whatever you label it, I don't care as long as you know what it is. All right, then you have I need a little bit more space. The ground pushes up on the chair. We'll call that the normal force. The ground is literally holding up the chair. And then there's one more, and I need to make sure my arrows are actually accurate here. One more, and we'll call that force of gravity. What's the net force acting on your chair? If I added up all those vectors, what would it be? It'd be 0. So I need to make sure my arrows corresponded to that. The better your picture is, the more useful it is. So, anyway, where you zoom in matters. Where you zoom in matters. And I'm specifically mentioning this because there's a problem I really like in the problem set related to forces. After today, I think you'll be able to solve it. Scroll, scroll, scroll. It's this guy. I like that problem a lot. Because of this. The mountain climber guy. This one, you zoom in on 2 different parts of the problem for part A, you zoom in on one point. At part B, you zoom in on a different point. But then they're connected together. So I mentioned that now because of that and because it applies to this one. So this one says to find the tension in each of the 3 cables supporting the traffic light if it weighs 200 newtons. So I want to see if you all can figure out where to zoom in first. And here, I'll zoom in on the picture so you can see. We have T1, T2, and T3. You need to decide, where am I going to start this problem? All you know is that the force due to gravity, we call it weight, is 200 newtons. You know that the force due to gravity acting on this light is 200 newtons. And yeah, these kind of problems, civil engineers, mechanical engineers, you need to be able to, this is statics. When you all take statics one day, this is all you'll be doing. Statics means not moving. Net force is 0. Eventually you'll learn net torque is 0. It's also not rotating. We're not going to bother with torque to the end of this semester. So, see if you all can determine where to focus in. I'll give you all like 30 more seconds to see if you can figure out the place to look at, where to draw a free body diagram, and then I'll kind of show you that, and then we'll move. Then I'll let you continue to move forward in this. Oh, yeah, no, stay zoomed in. It is advisable to draw this picture on your paper unless you want to be rubber banding your neck left and right every time. Or, pull up it on your slides. Make yourself work less. Don't have to keep looking left, right, all over the place. It takes less time just to draw it. It's good. You know what's fun? More fun than that? Double math. So where to focus generally is where do we have the most information? Where do we have the most information? So we are going to focus on the light first. We are going to draw a free body diagram of the light. Here's the light. Tension 3 pulls it up, and the force of gravity pulls it down. And then I'm going to let you all see if you can find T3. And once you find that, we're not done with the problem. It says in each of the cables. So the goal of this problem, kind of jumping to step 2. Step 2, step 1 honestly is just Fg equals 200 newtons. That's we know some angles. Those are kind of drawn in the picture. Those are tricky to write in your givens. Step 2 is what is T1? And I'm actually going to write this. What is the magnitude of T1? That means the x and y together. What's the magnitude of T2? X and y together. What's the magnitude of T3? X and y together. That's what this problem is asking for. You could express it in vector notation if you so desire as well. That's fine. You will have to do things in x and y. But yeah, T3, you can probably just guess what it is based on this picture. But I'll kind of write it out more rigorously. But once you all get that, see if you all can move onwards and figure out T1 and T2. You will have to draw a new free body diagram. You will have to zoom in on a different part of the problem. A part of the problem where T1 and T2 actually show up. Because I like y'all so much, I'll even tell you what equations to use. It's the same equations you're going to use like in every single one of these problems. The sum of the forces, F net equals F1x plus sum of forces in x, sum of forces in y, F net equals MAX, MAY. And I'll even write that a little nicer. So F net x equals sum of forces in x. F net y equals sum of forces in y. F net x also equals MA. F net y also equals MA. Oh, there's one more given. What was our given in this problem that was secret? It's not moving. What does that tell us? That the net force is 0. Or, I'll let y'all jump to that step. A is 0. Technically, the initial velocity is 0. All that jazz you kind of know as well, but that's not very useful in these problems. All these problems boil down, though, to sum up all your forces in the x, sum up all your forces in the y, set them equal to MAX, set them equal to MAY. That'll make your life easier. Well, easier. That's literally how you do these. There is no other option. And what I'm going to kind of be going around looking for is how is your second picture? If you have to draw another free body diagram. If you can't draw that second free body diagram, you won't be able to move forward. So that's the first step we're kind of looking at. Second free body diagram. So draw a box. We always start with a box. And where do you think we want to zoom in? Where do we have T1, T2, and other information all together? What part of the picture? So if we look at that part, we have to either pick here or we have to pick here. If we pick here, T1 is going to pull down from the ceiling. Do you know how much the ceiling is pulling back on it? It's equally. So it doesn't actually tell you anything. Is there a part of the picture we can zoom in where we do have some information? We have T1, T2, and some other piece. Yeah. That's where you're going to draw a free body diagram on. The second part you're going to zoom in, and I'm going to do this in green. is this right here. That intersection of cables. There doesn't have to be a physical object located where, I guess there is. There's a wire here. That's where you're drawing your free body diagram of. Why? Because we know things at that spot. It has T1. It has T2. And we just found T3. If y'all didn't find T3. So y'all can see in this picture, T3 is going to be 200 newtons because F net equals MA. So if we kind of wrote down that. So in this one over here, F net equaled T3 plus negative FG. F net was 0. F net equals MA. Well, A is 0. So therefore, 0 equals T3 plus negative 200. Ta-da, T3 is positive 200. Okay. This one over here, this little intersection that I'm going to kind of do in green. Boom, there's that. We have T1 going up to the left. We have T2 going up to the right. And we have T3 going downwards. You need to draw your angles on here. You're just going to need them. So there's that. There's my 63 degrees. So yeah, this is what we're going to work with. This is the picture. You have to focus on the part that has what you need and has something that you have. That's the key to doing every single one of these. When y'all get to statics, you're going to be doing this several times and then building. You're going to build a system of equations today, actually, with this. It'll be a great time. You'll say, wow, this is so much fun. I sure wish I could have a whole class on it. And your prayers will be answered in statics. All right. So the next step to give you all what we're going to do next. It's these equations, y'all. F net x. Sum up so break everything into x and y components. Find the x component of T1. Find the y component of T1. Find the x component of T2. Find the y component of T2. You don't know the number for T1 and T2, so you just leave it as T1. You leave it as T2. And you are going to go ahead and set up these equations. We do know something. What is the net force in the x component going to equal? 0. F net x also equals max. The net force in the x is 0. The net force in the y is 0. It's not accelerating. So, F net equals 0 equals sum up all your forces in the x. F net y equals 0 equals sum up all your forces in the y. That will make two equations for you with exactly two unknowns. T1 and T2. But you have to break them into the x and y components. That's the way we generate two equations. That's the only way we can navigate this. So, try to build those equations. This is the part I'm kind of leaving to you all. This is the last step of the problem. Set up the equations and then do the math. This is the last physics step. So I'll go around. This is when we'll go around and really kind of help you all if you're struggling. To the right is positive. To the left is negative. Up is positive. Down is negative. This is a vector problem, y'all. That's all this is. We basically made it into a vector problem. So, see if you all can set up that equation. See if you all can find T1 and T2. I'll put the answers on the board so you can know if you're doing it right. And its magnitude, so you're going to have the pleasure of combining them back together again. Boom. There you go. Do not use these answers to figure out how to solve it. That's a bad decision because that's not how the test works. Use these to check your final work. Do not use these to try to get the next step. It's just not a good strategy. Yeah, call us over if you're stumped. I'll be circling around. I'll be asking you all questions. But it's a lot easier to help you if I know you need help. Alright. Does it make sense why they look that way? Like why we drew that second picture? So we focus. T1 pulls up to the left. T2 pulls up to the right. T2 pulls down. Go ahead and just break them into components. Break T1 into make a triangle. So to get the x and y, you need to make a triangle. And there's many ways to make that triangle. Here's my T1. Here's my 41 degrees. That's my T1x. That's my T1y. Vectors. It's just breaking vectors into x and y components. No, you don't know what T1 is yet. So, but set it up with T1 as a placeholder. Yeah. Find the x and y components. It's setting up right triangles, and it's doing SOHCAHTOA. You don't actually know the value of T1, so you can't actually get the numerical value of T1x. You don't know the value of T1, so you can't get the numerical value of T1y. But you can still set up the math equation for it. What equation would you use to find the x component if you did know T1? Yeah. Oh, no, we're talking about breaking it up. This is the y component for you. SOHCAHTOA. Nope. That won't equal the sum. That will just give you the T1x. You're going to then do that for T2. So in this example, T1x equals T1 times cosine of theta. Cosine specifically of, not because x is always cosine, but because that's the adjacent side. Then do that for the y component. Then do that for T2. And then sum them all up. Right is positive. Left is negative. Up is positive. Down is negative. You are setting up a system of equations. This is an incredibly important skill for you all to be able to work in variables because it's very common for this to happen.
Yeah, I forgot my calculator. So
Oh my goodness.
I didn't just mess around with my phone calculator, but I got the equation.
That's real. Yep, that works.
Yeah, so I got 9.
Okay, okay, that works as well. Yep, perfect. How are we doing over here? Right. Where are we confused? Does it make sense how we get the x component?
Yeah, it makes sense.
Okay. So then, to kind of write these out over here, y'all, here's what you're doing. These ones right here. So f net x, if I take this first equation, the f net x is 0, equals f1x plus f2x plus f3x. Do that for this one. For the y component, f1y plus f2y plus f3y. I put these all as plus. You have to, some of these will actually be negative. I put it in the general form. Some of these will be negative. For example, t1 points to the left. So the x component of x, the f component of 1 points to the left. And actually, yeah, I put f's here. You could put t's. It really doesn't matter. If you're like, where do these f's come from? T1x, T2x, T3x. I am writing it in the general form where you add them up. But some of these are to the left, so they're negative. Some of these are downwards, so they're negative. Don't forget to put your positives and negatives. I put it as plus because that's the general form, and I want us to get used to that first step of you add them all up. But then you have to make that additional step of sometimes it's negative. And make sure you can do that.
Yeah, it is. But I think for the y, it's all
So like T1y and T2y. Okay. So to just, build our things, we have T1x is T1 cosine theta. T1y is going to be T1 sine of 41. If you repeat the same thing for T2, you draw a nice picture of it. T2 is up to the right. This is 63 degrees. You got an up, you got a right. Do the whole shebang. T2y will be T2 times sine of 63. T2x is going to be T2 times cosine of 63. Not because x is always cosine, but because of the triangle. Not because x is always cosine. I'm going to stress that again and again and again because it's such a bad habit that people get into. And then the last one that we haven't listed is T3. T3 has no x component. The x component of T3 is 0. It points straight down. T3y is 200. Notice I am putting these all as positive right now. This is my way of doing things. You do it your way. I put the negatives and the positives once I plug it in. I put the negatives and positives once I plug it in, not beforehand, but you do whatever works best for you. You just need to make certain you do it at some point and don't do it twice. All right. So the last physics step is to literally just take these and put them in the equations. So 0 equals T1x. This is when I decide positives and negatives. For me, you could have decided earlier. T1x, does it point left or right? Left, positive or negative? Negative T1 cosine of 41. You could have decided to put that negative earlier if you were afraid you were going to forget. That's fine. Just don't do it. Don't count it twice. Make certain you include it. Plus my x component of T2, T2x, positive or negative? Point to the right or to the left? To the right. Here it is. It's pointing to the right. So that's positive T2 cosine of 63 plus, what's my x component of 3? 0. Boom. Great, that's an equation. Then we do it for the y component. Actually, you all do it for the y component if you haven't done it already. Set it up, system of equations, solve. This is how you do every single force problem. Draw a free body diagram. Split them into components. Sum of x equals max. Sum of y equals may. One of them will. This one probably does. Yeah.
Okay. Also, to everyone, I will be at the physics help room on Wednesday, sometime after 3:30, maybe earlier, depending on our taking guys out. But I will be there then, since another class has a test coming up on Thursday, so I will be helping then the best I can. So if anyone wants to come over and drop by on Wednesday at around 3:30, we have time. I'll be there probably around an hour. Have a lot.
All right. Now we go on and set up the y equation. Yeah. 200 is the point up or down? Yeah, good. How are y'all doing on the y component? He's a great resource. It's like, make use of it. Make use of it. This is one of the things I want you all to find people around you that know the stuff that pick it up quickly. Use them as a it'll help them learn it better too. And it's exciting. Alright. That one actually was fine. Oh, yeah. The way you drew it, so the 41 degrees is up here. You drew the 41 degrees down here. You can do that, but you'd have to do 90 minus 41 to draw that. Alright. So to help y'all check your work, this one is positive T1 sine of 41 plus positive T2 sine of 63 plus. It all comes to, this is just a vector problem, y'all. Once you can kind of connect this to what you practiced the first week, it's vectors. Break it into x and y. Add up all your x's. Add up all your y's. The thing that's maybe a bit different in this problem, you didn't actually have the numbers for T1 or T2. And so that's a new skill. Working with variables. Working with placeholders. That is a skill. Again, if you all continued on to be physics majors, you would never see numbers again. Okay, you would see them, but they would be like multiplications. They'd be just constants that get multiplied. You never solve for numbers in upper level physics classes. Yeah. Exactly. Yep, in our picture, T2 or T2. Yep. Yeah, so maybe I could have. That one's negative. You know what? I'm going to let people be. They're going to have to think a bit more if I leave it as is.
Oh my god.
All right. How are we doing? You have 2 equations and 2 unknowns. Yep. once you set this up, two equations, two unknowns, three equations. There's several ways to solve it. Yeah, I gotta do the no, I have a watch for it. Oh, it's at 9:30. No, that wasn't my sense. Don't worry. I set the line for these things. 8:20. I have a alarm for it. I don't know why my 8:21 didn't go. So no, it's been in the back of my mind. And while y'all are having so much fun.
Oh yeah.
Oh, how'd the lab grading go?
Yeah. This time it's a lot shorter. Last time, accounting for like 40 minutes.
Great, perfect. That's what I'm hoping for. I'm hoping like around the 30-minute mark kind of thing. Yeah, so we'll have our test this next week. I'll probably start this back with you. So it's going to be a 2, so it'll be 3 free responses, rubric 4s. It's very much though is yeah, and it's rubric 4 is literally just to help them. It's a problem solving process. How many steps in the process they did, and basically have 20 points on how much they did. So that's that. I put that there for their sake, but really it's just to clarify. Do the problem solving process. You get points based on each of those steps. On the lab?
Yeah.
In the future, we'll just keep our eyes out for that. It is what it is. Do you mind if your phone isn't working, call over person. The attendance thing is blinking at you. I was hoping the flashing lights would catch people's attention. So make certain you all do that. The blinking light. It counts as blinking. It's white and black. That's blinking. But I want to see this. So you can't actually add any of this. There's a T1 in front of this, and a T1 in front of that, and a T2 in front of that, and a T2 in front of that. Nope. And this doesn't equal X, this doesn't equal Y, this equals Y. What is my net force in the X direction? And the thing is not accelerating at all.
Hello.
What's my, if my acceleration is 0, what's my net force? 0. This all equals 0. This all equals
Can people hear me? Okay. Really quick attendance tip that I just got from one of the students. If it doesn't work, I don't know.
That's not working.
If it doesn't work on your phone, you might be able to try it with your computer webcam. It worked for some people. It might work for you as well.
There you go.
But otherwise, put your hands up and I will write your name down.
And it's probably not going to work out the way. So I don't want to set up both people against each other. 2 equations, 2 unknowns. Yep, manipulate it, solve for one of them, plug that into the other one. Yeah, it's a bit of a chore, but it's how you solve it. There you go. It's me. Yeah. Here, you can bring it over to my laptop here if you want, or you can do it to the big screen. Let's see. You also might be able to. Do you have a web? No, you don't. Yeah, I do. All right. Will this work for you? Oh, look at that. We have a solution for the future. Let's go. Let's go. Let's make our life easier. Greg was like,
me on Sunday. If you go to OC's office hours, let me know so you can pass by.
Yeah. I was like, and yeah, make use of Greg too. He can teach you physics. And probably in a good way. I was like, he knows physics. If you ever need help, ask. I was like, I'm a resource. He's a resource. Use any and all resources to help. There's no way to do it. There's no way to use it. In fact, they're all reading. They both have the exact same. Yeah, and that's because C1 cosine 41 equals so based on that, you will see that T1 and T2. So the x components are equal. X components are equal. So the next step, y'all, if you're stumped on what to do now, it's a system of equations. So this is just a math problem. This is like, and I say that not to insult you. I say that you've done a lot of math at this point. So all I got to convince you, one of the things that gets tricky whenever you get to class is sometimes you forget you know things. Sometimes you forget you know things because in a new context, you're kind of stuck in that new context and you forget that you have a whole bunch of other knowledge. So to that end, these are just two equations with two unknowns. How do you solve this? Solve for T1. So isolate T1. So in this case, T1, you're going to add it over. You're going to do some algebra. And I'm going to let you all prove this for yourself. T1 equals T2, cosine of 63 over cosine of 41. And then what do? You plug that into the other equation. It's two equations, two unknowns. Solve for one of them in one equation, plug that into the other one. You all have done this at some point in your life. There's no way you got to my class without having done this. So I say that not to insult you, not to saying how dare you not realize this. I say that you know how to do this. You just have to remember that you know how to do this. You just need to remember that you know how to do this and make that connection that when you all get to step 4, it's just math. It's just math. There's no physics that we're doing at this point.
Also, for anyone who needs attendance, who didn't get it, you say here, raise your hand. I will not get you.
Yeah, you can
okay.
You can like divide the 2 places. It's one way. Well, that gets a little messy. So yeah, there's many ways. If you get the right answer, it works. All right. At this point, y'all, we're gonna move on. If you had challenges with this is a great vector problem, force problem. This is a great problem to practice because it's foundational skills. The only physics stuff was net force equals MA, net force equals the forces. It's not C1x. I know. C1x equals this.
I think more people miss this.
Yeah. That's really good. And that's for the notation. If you're careful with your notation, I will. Yeah. No, so you have to take
Wait, like quick one?
and then you plug it into
right
the
now
other
we're like, okay, you like solve for one.
So you put on C1 here, you just take this and
There's an
put it right there. And now it's just now everything's in terms of one variable. So I'm going to leave this math part for you to do on your own if you haven't finished it yet. And you can ask questions to me or other people. The physics is done. But of course I can still help you all.
Oh, yes.
All right. let's see. This is basically just, I haven't asked a clicker question yet, so let's ask one. What is the correct free body diagram for a car at rest?
Because generally people learn how to do it.
Yeah.
And it's easy to tackle steps. But when you have multiple voices like that, you can't do that both of each other and just can't take people.
Yeah, these ones I don't think quite cancel. Yeah. There's many ways to do these algebra. Yeah, you can be creative and learn to multiply a whole equation by something so you can add equations together. Oh really?
Yeah.
That's how you were taught to do those?
Yeah.
That is a much harder way. Like, it becomes, you can eventually make it intuitive. Yeah, that's the other way is more like we call it the brute force. Sure. Some of them will. I did have one student who had a problem where he used his calculator to solve it, and it uses the quadratic and gave him only one of the possible solutions, which was fine. But it was the problem was what's its velocity when it's 3 meters high and there's a projectile, and it gave it on the way down versus the way up, which was a correct solution, but it wasn't. He was like, "Why is mine negative?" So that's the challenge whenever you use a calculator. It's a black box that you put it into, and when you have quadratic, there's things like that can turn up. Yeah. Otherwise, you can run into problems like that. All right, we're gonna go for just 10 more seconds. This is a fairly straightforward problem. 5, 4, 3, 2, 1. Yeah. We're learning our forces. Great job, everyone. So good. I can click it eventually. Bada bing, bada boom. All right. What's the correct free body diagram for a car traveling at a constant 23 meters per second? We have a constant velocity, therefore our acceleration is 0. First one, I guess, if you weren't overcoming the possibility, assuming you're not hitting the gas. Oh, so what I did for this Thursday, so I posted that one. What I did for it is I did the same for one of the procedure, but I hit the procedure on another assignment. So I will then post the link to the correct procedure, and it'll have the right exactly what to do. Because this is a skill I want them to practice. It's not really graded to points or anything like that. But so it's we need a set procedure so it's easy to grade. But I want them to practice coming up with a procedure that's useful. Yeah. That'd be good. So I have about, at this point, I've been able to mooch off of fake slaps. All right, y'all got 10 more seconds. When we start getting onward, I'm going to start running out and have to make my own. Which is unfortunate. He only has 8 labs, and we have more weeks than that. We have like 10 or 11. So I need to make 3 weeks of labs. So I may throw that out to you all if you have any ideas of experiments. All right, 3, 2, 1. All right, free body diagram. Let's just draw it from scratch. Boom. Yes, there's still gravity. That doesn't disappear. Yes, there's a normal force. The car is pushing, it's like you are hitting the gas. You are pushing the car forward. There is an applied force. The reason you're not accelerating, though, is there is a friction force. Just because forces cancel doesn't mean we don't draw them. And that's the distinction I wanted to point out here. Just because forces cancel doesn't mean we don't draw them. Case in point, FG and FN cancel, we still drew them. Just because they cancel, we still draw them, and you all largely did a good job with that. But if you missed it, that's okay. Even if forces cancel, you still need to draw them. Okay. This problem, the pulley problem, the classic. Right, classic. All right. I'm going to walk us through. There is 2 ways to do this problem. There is 2 ways to do this problem. So this problem says, I have 2 masses connected by a string. At all times, this string is taut. It's tight. That string is never loose. So it is currently on a frictionless surface, but I am fairly confident. I don't know if I put it in the slides, and I'm not sure. Let's see. Did I put it in here or no? Oh, I need to add this. All right. I need to add an extra component to this, so I will add it at some point. This problem currently has no friction. Once we learn about friction, I will reintroduce this problem with friction. It doesn't make it that much worse, to be honest. It sounds worse than it is. All right. They're stuck together. Mass 1 is 4 kilograms. Mass 2 is 1 kilogram. Frictionless. The table and the pulley are frictionless. Find the acceleration of the system. My first question to you all, and this is where we're actually going to spend the most time. Doing the math is fairly simple once I show you all a couple things. Where do I zoom in? Where do I draw a free body diagram? And there is 2 answers. It is possible to answer this problem by drawing 1 free body diagram, or it's possible to draw this by drawing 2 free body diagrams, and both are valid options. Both are valid options. I want to see if you all can figure it out. There is 2 ways to do this. Both are correct. One way is by drawing 1 free body diagram. The other way is by drawing 2 free body diagrams. Discuss. Determine. Figure out. Talk to your peers. This is a brainstorming session. How do? Where do you want to zoom in, and what forces are acting on it? The other way is no one's gonna unless they think this is more than not realize the second one. Yes, that's. Yeah, because it's the same string. And opposite, if that would pull that. No, gosh. Okay.
We did though.
Yes and no. Yes and no. Yes. Actually, yes. There will be pulleys. I'm not going to tack it onto like this one. Oh my gosh, that'd be nice. Like, no, I'm not going to like say this pulley down, but I will have like hanging pulleys and stuff like that. Much simpler. Much simpler.
Yeah, I remember we did this calculating the velocity to get the velocity of the velocity, I think. But that only works if the pulley is at they're usually flat. Yeah, oh my god, it's so I'm hating that problem so bad.
You guys take one object and just call it Yeah, you never. If you have 2 objects, they should be like stuck together. I'm going to tell you all that drawing the 2 free body diagrams is the one that's going to be more aligned with what I've taught you so far. To be able to draw 1 free body diagram, there's a trick to it. There's a trick that I've kind of mentioned, but you have to realize something to do that trick. So I recommend doing the 2 free body. You should honestly be able to do it both ways. That shows expertise. But do the 2. I recommend drawing the 2. And it's really easy to choose what 2 if you're going to draw 2 free body diagrams, it's fairly, hopefully straightforward what 2 areas you're going to focus on.
I would not say that.
So, if this thing was 3 meters in 1 second, how many years is that? So the acceleration of this guy is because they are literally stuck together, even though it's x and y. Even though they Is there any force pushing these also? There would be. So, if you haven't realized it, the two object one, so where are you going to zoom in? Zoom in on this object, draw a free body diagram. Zoom in on this object, draw a free body diagram. So draw two free body diagrams for mass 1 and mass 2. Draw all the forces acting on them. This is the way that kind of connects how I've kind of taught you up to this point. No tricks involved, just kind of straightforward. Draw the forces, draw some arrows, label them. Label what those are. If a string is pulling something, we call that a special, there's a name for those forces. When a string is pulling something, there's a name for that. When gravity is pulling something, there's a name for that. When a surface is pushing something, there's a name for that. Using those names will help you. What forces? So looking at mass 1, what forces are acting on this? Don't overthink. It's not a crazy question. Is there anything pushing or pulling? That's what. And what do we call this is very attachment? What do we call the forces? Well, attention, the way it's pointing. Right. So that's literally you're just kind of keep going straight. So when you're doing these, it's literally just mass 1. What's pushing or pulling mass 1? Gravity is pulling it down. Sure. Yes. What else? The rope. What do we call the force that a rope pulls on something with? Tension. Which way is that rope pulling it? For mass 1. For mass 1. To the right. The rope is pulling it to the right. And I'm just going to call this tension. All right. Any other forces acting on this? Normal force. And the normal force will be exactly equal to force of gravity. They cancel. Fantastic. Great. We're done with that first free body diagram. Mass 2. What's affecting that one? Gravity. Now, I'm going to call this FG1. Just to clarify these, this one's FG2. All right, what else is affecting mass 2? Tension. Which way is that pulling? Is the rope pulling it up, or is the rope pulling the thing down? Which way is the rope pulling it? The rope is pulling it up. That rope is holding it up. It's not pulling it, and that's the way to think about these. Which way is it pulling? That's all forces are. Now notice I called these both the same T. If this rope pulls this thing 3 newtons, Newton's third law, for every force, there is an equal and opposite. If this rope pulls with 3 newtons, guess how much the other one's going to pull with? 3 newtons. They're the same rope. Tug of war. If I pull one end with a force, the other end's going to pull the wall with that same force. A rope is just a way. The T is the same because it's the exact same rope. It's the exact same rope. If one pulls on one end, the other pulls on the other in the exact opposite direction. So, how is this useful? How is this useful? We set up our F net. Remember, M1A1 equals all the forces acting on it. M2A2 equals all the forces acting on it. Technically, X and Y, We have to split things into x and y. But what do we, and mass 1, what happens to the force in the y direction? Do we care about them? These forces cancel each other out. You could write the equation for it, but they cancel each other out. They do nothing for us. So, if we sum up all the forces for mass 1, we get M1A1 equals T. Literally the only force that doesn't cancel out is that one. Set up the equation for the mass 2. And again, technically x and y, but we're blessed that this equation doesn't have x and y components. This problem could be much worse. You could put a pulley on an incline, and then you have x and y components, and then it's just a bunch of extra math, in my opinion, for little benefit. So see if y'all can set up the equation for the second object. So M2A2 equals T. Does it point up or down? Up. Positive or negative? T plus FG2. Does that point up or down? Down. And you know what? We know what FG equals. But it should be negative. Okay. Now, you kind of have two equations and two unknowns, but I'm also going to reveal something to you all that maybe you didn't realize. I've been putting A1 and A2 this entire time. I've been putting them as separate. What I'm now going to challenge you all, you know what? Let's see if it, I'm going to make you all think about it. How does A1 compare to A2 in the following problem? Does A1, is it greater than A2? Is A1 less than A2? Or is A1 equal to A2? Boom, there's the problem, there's the picture. Do. Think about it. Okay, we got this one. It's a really good point. I guess that friction teach. Yeah, this client playing circular stuff. So we're probably gonna have to do all the time. I don't know what. All right, what say y'all? Why? Two objects stuck together, everything, their position, but everything else is the same. Alright. That's a good one. So, yeah, let's think about what that would be. If A1 was accelerated more, what would happen to my rope? It would get loose, but that's not, yeah. They're stuck together. That rope is always tight, and you can think of this as a real world problem. That rope will never get loose, unless like the bottom one hit the floor and stop pulling it. At which point, yes, then they'd have different accelerations. Yeah, so this is the crazy thing when it, as crazy as it seems, it's a one-dimensional problem. As weird as it seems to realize this system is stuck to a rail. It can literally only move this way, and that's one dimension, even if it doesn't seem like one dimension. All right, we'll close this out in 5, 4, 3, 2, 1. All right. Very happy to see the responses here. It looks like discussions were good. They are equal. They are literally stuck to each other. This is a taut rope. It's basically, you can imagine it like a rod. Or, something like that. So They have the same acceleration. So A1 and A2 are the exact same value. A1 and A2. If they weren't, this is two equations with three unknowns and you can't solve it. But through the magic of these being the same, two equations, two unknowns. Great. Okay. Before you go off and solve this is just math at this point. The math isn't very interesting. It's just doing math, find the tensions are the same, solve for A, awesome. I am now going to show you all, you could do this problem with a single picture. You can do this problem with a single picture, but it requires you recognizing what we just talked about. They're stuck together. They're stuck together. Whatever happens to one, happens to the other. So, and something I'm also going to challenge you all with, as crazy as it seems, this is a 1D problem. This is a one-dimensional problem. These are on rails. You know, it's like a ride. If you go to any theme park and you go on rides, they're on rails. You may be making left, rights, and all that kind of stuff, but the reality is there's only one path you can take. You cannot deviate from that path. By definition, that's a one-dimensional problem. You can go forwards or backwards. It might turn and do all that crazy stuff, but as crazy as it sounds, if you are constrained to a path, that's a one-dimensional problem. As crazy as that sounds, because one-dimensional means that you're constrained. You can only go forwards and backwards. You cannot deviate from that. As crazy as it sounds, if you're on rails, it's a one-dimensional problem. Why do I say that? Here's the free body diagram that we're going to draw for this. Let's just get rid of that rope entirely and stick my two objects together. If we do this, what this problem ends up becoming is, let's just imagine that gravity is pulling to the right instead. Pick a direction. It really doesn't matter. Right, down, whatever. Let's just pick it to the right. That is the free body diagram for them stuck together. You can conceptualize this problem as two objects stuck together being pulled with this force, because it's the exact same thing. Two objects stuck together pulled with this force, because at the end of the day, if you all look at this equation, my tensions cancel out. If you all solve this problem, you end up finding the tensions can't. So if we solve this problem, let's go ahead and plug this in here. So M2A equals M1A. Literally all I did was just take that and put it here. Plus negative M2G. If you rearrange this, you get M1 plus M2 times A equals M2G. Did I do some weird things number-wise? Am I missing a negative somewhere? They should end up being that way. I feel like I forgot a negative somewhere. I messed something up. Well, anyway, that's what it ended up being. Yeah, that sounds like it shouldn't be minus, though. So I'm like, I'm not sure where my minus came from that I made a mistake on. Oh. Okay. Here's why. This is a little subtle. This is why. This is subtle. A here is technically going to be negative, because which way is mass 2 going to fall? Down. Which way do we find down as? Negative. Which way is block 1 going to move? To the right. Which way do we define that as? So technically it does end up being that A1 is negative A2 based on coordinate systems, and that results in this working out for us. Whatever. What I want to challenge you, though, this is one way to do it. Tensions cancel, but you have to realize this. This is the much easier way. If you realize, I got two blocks. One of them's being pulled by gravity, but they're stuck together. The other one, nothing is happening to it. And so this is your free body diagram of it. And let's just set this up. This says that the total mass. So I want you all to set this up. So F net equals MA. And F net equals sum of forces. Set this equation up for me. Set up the equation to solve for A. what is my total mass of this system? What is the net force acting on this system? See if y'all can set up this equation. Yeah. That M is a total M. Some of the forces are the only forces acting on it. Yeah, it's just setting them equal to each other. So this first one is M1 plus M2 times A. What's my total mass? M1 plus M2. There's two objects. You got to add them together. What's my forces acting on it? FG2. These two things are the same. So, M1 plus M2 times A. Ta-da! And it's the same answer we got in the last one. All a pulley does is basically make a Y force into an X force. A pulley redirects forces. That's the purpose of a pulley. A pulley takes a force in one direction and makes it go a different direction. That's why they're useful. I can pull a pulley down and make something go up. Or I can pull a pulley down and make something go right. A pulley is used to redirect forces. So I really challenge you all to think about this problem. What I'm trying to convey here isn't math. It's a concept. You can do the brute force method of two pictures. You then do have to realize that the signs of acceleration are opposite to each other, which is a really subtle thing. You can do this way. This is great. But if you can recognize that these are two objects stuck together, and all I have to do is draw the forces, I can basically pretend that rope doesn't exist. Pretend that rope doesn't exist and pretend these two objects are stuck together. What makes them move? Only the force of gravity on the second block. And nothing else affects it. Nothing else is affecting it. And you can make this system here. So my challenge to you all will be with this one. What if there was friction? So when we get to friction, we'll revisit this problem. And what do you do in that situation? At this point, we'll jump into our break. We'll reconvene at 9:27. Feel free. You can solve this problem more in detail. If you don't do it now, you're going to want to do it in the future. So it's up to you. But you got 7 minutes. Give your brain a break. Or if you're feeling okay, solve the rest of this problem. Up to you. And after this, we'll get to inclined friction and inclined planes. It'll be a good time. Yeah, after the break. Yeah. I got my alarm.
I missed the icebreaker question.
Okay.
Because I was taking a call for someone who's scammed me out of $5,000.
Scanned you to find.
Yeah.
What? Oh my gosh! Just shoot me an email. Just shoot me an email. But I'm sorry that you. Oh my gosh.
I was closing a land deal.
A land deal?
Dumbest shit ever.
Okay.
Yes. And I guess the little guy, the realtor.
Yeah.
Person, to 7%.
Okay.
This stuff, the beautiful 5%.
Okay. Was that like a contract or something?
Yeah, so it was the first time that I ever did something like that.
Sure.
Online.
Sure.
So.
Yeah. Oh, that's not fun. That's not fun. Hopefully you made something at least, but 5,000 is a lot.
So this question, if you want to draw it as like a one, are we drawing the normal force basically the whole impact versus gravity?
So there's actually there is no force forces.
Right, but like when we're solving M1 plus acceleration, it's kind of like Fn equals mv.
So it's not Fn equals it's MA. So it's the two equations always are bread and butter. F net equals MA.
Okay.
And F net equals the sum of the forces.
Okay.
MA, if my two objects are together, my mass is an M2. My mass is an M1.
Right, it's combined.
It's combined. So that's where that comes from.
Oh,
It's literally just yep.
It's
they're together, so therefore their total mass M is M1 plus M2.
Okay.
Um,
Gotcha.
so if we want, we could like put a big M here to clarify.
That makes sense.
Yeah,
Okay,
yeah,
thank
yeah.
you so much.
And then you just boom, and that's the only thing affecting the system. So this one pulls it, but the other mass, its contribution is it makes it harder to move. That's its only contribution.
Right.
Now, when friction gets involved, you literally just boop, chuck a thing of friction on there, which will.
How about if we did like some sort of problem where we had to draw like a pulley with a box over here, and then the line would be curved because there'd be like two rollers?
Ooh, okay.
Would that have the same sort of effect, you think?
So in that
With-
case, this if you drew those two together,
Mhm.
this one is also contributing. There's actually a force pulling this one down as well,
Mhm.
but they'll still line up.
Okay.
So in that case, you would get FG2 and you'd get FG1. And you'd have to
Oh.
find, because it's down an angle, you would have to find the component of gravity that points down that angle.
Okay. That
Yeah,
makes so much
yeah,
sense.
yeah, yeah. But that's exactly, yeah. Because they're stuck together, you literally can, and it's a one-dimensional problem, as weird as that seems.
Yeah, that is crazy.
They're constrained. If they're constrained to a straight path, doesn't matter if that path is wiggly waggly, that is the definition of 1D.
Okay. One last question.
Yeah.
So about the quiz, I realized my problem was this is so
Okay.
for the F final.
Yes.
My problem was when I was signing solving for time. Did I have to have my final velocity as negative? Because if I subtract the initial velocity from the final velocity, then I got 2.1. But if
Yeah,
I added
so-
them together, then it was actually.
So you have to realize
That
the
negative.
question is are you going up or are you going down?
Right.
Because when you solve this, it doesn't. Whenever you square root, the answer is plus or minus.
Yes. Yeah, you're right.
So you actually, it could be on the way up or it
Oh,
could
I
be on
didn't
the
think
way
about
down.
that. Yeah,
and
I
you
didn't
have
think
to
about
think
that.
about which is the right answer. Yeah, yeah, it's one of those subtle things that equation does.
Right. So final velocity would be negative because
If
it's going down.
it's going down.
Yeah.
If it's going
because the ball
down.
goes up and then goes down.
Yeah, depending on where you're at in your path, because at some point it is positive.
Right.
At some point you are going up,
positive.
and at some point you're going down. So yeah, if you draw the trajectory, there's there and there, and you have to decide where am I? Am I in the beginning or the end?
Right.
Yeah.
Okay. Thank you so much, Dr.
Yeah, no
Davis.
problem.
I appreciate it.
What's up?
Explain in this problem like how you would calculate the tension in the rope.
Oh, sure. So you actually don't need tension in this at all.
Isn't that one of the questions?
Oh, is it?
Yeah.
Find the tension. Oh, once you have this, once you find A, you can just use this. You can just zoom in on one of them.
Okay, so tension is just the mass times.
Yeah, you then just draw a free body diagram of either this one or this one.
Okay, so in like which mass is it?
Depends which one you pick. You can find tension with this equation, or you can find tension with this equation.
Okay.
If you use this equation, you have to realize that acceleration is down and to put it as negative. If you use this equation, acceleration is positive. Yep. Yeah. Let me jump over here. Yeah, stand up, and then I got you next. Very weird. But that's a great question. Was there any Alright, this is like I'm slowly walking away, but all right. So we're back at it again. Resuming. So the other part of this problem that's really good is part C. Part C. So once you get the acceleration and the tension, awesome. Part C is a kinematics problem. The reason part C to this is really good is it's actually very easy. Part C though is very good because it's a kinematics problem. Your acceleration will not be g though. In this problem, your acceleration isn't g, it's whatever you calculate. So do work through these problems, y'all. I know our test is so we're gonna finish this problem set by this Thursday, and you have the test after that. And also the quiz for forces is not due until after the test. Do not wait until after the test to do the quiz. Because let's think about it. If you wait till after the test, the purpose of the quiz is to see if you understand it. It's not going to help you to determine whether you understand it after the test has happened and you already realized, oh crap, I don't understand it. When do you want to realize you don't understand it? On the test or on the quiz? Yeah, on the quiz. You want to realize you don't understand it on the quiz before the test. So if you wait to take my quiz till after the test, then you might realize you don't understand forces until you're taking the test and you say, oh crap, I don't understand forces, and it is what it is. Yeah. What day is the test? 26th. All right. So, practice these. All right, great. Spring force and friction. We already talked about spring force last class, so this won't be too bad. All right, so here's the spring force. Woohoo, it's Kx. Remember, x was the deviation from the equilibrium. It's not how big your spring is. It's not how big your spring is. It is how much it gets stretched or squished from its equilibrium spot, from where if nothing's happening to it. That's x. K is a spring constant. This number can vary wildly. You can have a really weak spring with 1 newtons per meter, or you can have a spring constant of thousands of newtons per meter. It depends how stiff your spring is. The stiffer the spring, the bigger K is. The weaker your spring, the less K is. The units for K are very easy to figure out. Let's derive them together. K equals F over X. I did not do anything crazy there. I just did some algebra. And there's my alarm to take attendance. I'll snooze it for 10 more minutes. Hey, what's the units for F? Newtons. What's the unit for meters? Or for X? Oh, look, you all just derived the units for K. It literally comes from the equation. The units for K are newtons per meter. They literally come from, just move the X over. Ta-da. K is pretty much always measured. If you buy a spring, they did not theoretically calculate K. They literally just did some experiments like you all did last time and they measured it. K is way too complicated to theoretically determine. It depends upon the material you're using. It depends upon how tightly you've coiled that wire, the diameter of the wire, how big those coils are. There is so many variables that go into the temperature of the room. K is actually going to change based on how hot or cold it is. Metal gets easier to stretch if it's hot. Anywho, experimentally measured. K is experimentally measured. And to make certain you all are comfortable with this equation, boom, 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 click, click, click. A spring has a spring constant of 50 newtons per meter and is stretched 1 centimeter. What is the force caused by the spring? Be careful. That's my only hint to you all. Be careful. I'm not going to even tell you what to be careful about. Be careful. If you can answer this in 2 seconds, you weren't being careful. How come? That's all I care about. Okay. Yes. That's all I care about. It is a question.
Oh, centimeter. It's 100.
You did it. Yeah, nice. Good, that's good. It's worth. I think it's KX. All right, I'm going to give you all 20 more seconds. The math here is simple, but you do have to be careful. And it looks like we are being careful. 5, 4, 3, 2, 1. All right, so F equals KX. This is my K. This is my X. But you should always convert to base units. Every single equation I ever give you is calibrated for base units. Every equation is calibrated for base units. If you do not use base units, it will not give you the right answer. So 50 times 0.01 equals 0.5 newtons. Obviously, 0.5 newtons is not the same number as 50 newtons. You can see why it matters. 50 is not 0.5. Those are two different things. So this is just... Don't forget to convert your units. That's what this question reminded you all of. All right. Let's see. If you pushed a box on a frictionless surface, fun fact, even if you can't stick to the ground, you could actually still push that box. You do not need friction to push something. You just need friction to not go backwards. If you push a box on a frictionless surface with no air resistance, what would eventually happen after you stop pushing the box? Would it stop? Would it speed up? Would it slide forever? Or who can really say? Who can really say? And the surface is infinite. It is a flat surface. It is a flat surface. Yes, that is good. But what a nice, what a good segue for eventually when we get to this. It's not as bad as it looks. I drew the arrows. It makes it look worse. It's fine. You'll be fine. You'll be fine. All right, 10 more seconds. All right, 5, 4, 3, 2, and 1. I lost 5 people. They're probably online. All right. What would happen? It would slide forever. Again, it's all about the forces. If you push it, when you first push it, the forces are gravity, normal force, and you pushing it. Later on, it's just gravity and normal force, and they cancel out. None of you all have pushed a box and it slid forever because friction exists. Boom, here's friction. Friction force is, it always opposes motion. Friction always opposes motion. And the equation for it is mu Fn. Mu Fn. And if you'll remember, there is no equation for Fn. Fn is based upon the problem and based upon how much it's touching something and gravity and all that stuff. So, mu Fn, it is always opposite the direction of motion. If you know the direction of friction, you know which way an object is moving. Or vice versa. If you know the direction of motion, you know the direction of friction. If you know the direction of friction, you know the direction of motion. And why does friction happen? It's because if you zoomed in on something microscopically, everything is bumpy. Everything. And in fact, even if it was perfectly smooth, there's atomic forces, there's van der Waals forces, and all that kind of jazz. So remember, when you get to a microscopic level, the electrons start interacting with each other, and that gets kind of complicated. So the easy explanation is everything is rough. You technically, even perfectly smooth surfaces will experience friction. If you somehow had a perfectly smooth layer, there is no perfectly smooth. Zoom in on an atom, and they look like spheres. Those are not perfectly smooth. The electron orbitals will kind of bump up against each other. It is impossible to get perfect. Like, perfectly smooth is this atomic smooth, but even that's bumpy. So, honestly, this is a good enough explanation, but at that point it gets really complicated. Whatever. The coefficient of friction is how this is a deceptively complicated idea. Decepticon-y. Yeah. Whatever. It is incredibly complicated because it depends on both materials. It depends on both materials. So, like, if I have wood on metal, that's a different coefficient than wood on wood. Different coefficient of wood on tile. Different coefficient of metal on tile. Different, like, every single two objects you have that interface with each other will have a different coefficient of friction. So guess how we calculate this? Experimentally.
Yeah.
You can buy a book, and it'll tell you the coefficient of friction between two different surfaces. Or, depending on what you're making, you might have to calculate this yourself. If you can't find it, say you made a new material, and you say these two, I want to make a bushing, and I need that bushing to have a certain coefficient of friction with something else. Then you would have to measure that if it's something someone else hasn't done before. Yay. All right. There's my alarm to remind me to take attendance again. Good job, alarm. Leo's going to go around with the paper again.
So raise your hand if you need it. I will.
Gives you some good FaceTime with Leo. Ask him how he's doing. If he tells you fine, that means it's not good. Ask him why. I think he's doing okay. I think he's doing good. I'm not actually saying he's doing bad until like. But pro tip: if anyone ever tells you they're doing fine, fine is not good. You should ask them why. That's caring. If they say they don't want to share, don't push them. Leo's doing better than fine, I think. Go ask him. I don't actually know. It could be really. I could have just done something terrible. I don't know. Yeah, what's this? This is like opposite. Okay.
It worked?
What? I think it's the 140.
Maybe a purple?
My Mondays and Thursdays are 11:10 to 12:10. I know the time is super awkward sounding. The reason for that is I teach it takes me 20 minutes to get this like after everything. And then the other ones are also slightly awkward sounding because I teach a class at 3, so it kind of lets me go right up to that when I have to leave for that. Instead of having like 5 minutes of useless time. All right, last chance to call Leo over. All right, friction. Fantastic. Let's see. Is this next question the one I want to ask? Yes, I love this question. Is it harder to move a box that's not moving or one that is already moving? I have not said anything like what's easier to. And let me rephrase this. Is it harder to accelerate a box not moving or one that is already moving? Which one is easier or harder to accelerate? Or is it the same? Doesn't matter. Go with your gut. Doesn't matter. It's on a flat surface. Could be moving towards the acceleration direction. Yeah. All about acceleration. Which one's easier to accelerate? Not moving or already moving? Same mass. Same mass.
Go. You see? It's easier. No. If you're not moving, do it again. No, push me. Oh, see? It's easier. I had to get out of my chair. I just like
It's good. It's good. Those are the things to think about. Even if you don't know, it's good to think you kind of know. All right, y'all got 5 more seconds. 5, 4, 3, 2, 1. All right. The key to this problem is it's all about friction. It's all about friction. When you are trying to move an object, what are you fighting against? Friction. When something's already moving and you're trying to accelerate, what are you fighting against? Friction. So this question is actually asking, in which case is the force of friction higher? And it is harder to accelerate an object not moving. There is 2 types of friction. There is 2 types of friction. Assume friction. The last slide said friction. The last slide had friction on it. I think I don't feel too bad about that. All right, let's see how we did. All right. So, why? So let me show you on the next slide. There's two types of friction: static friction and kinetic friction. Mu S and mu K. Okay. Mu S, static friction, these are numbers. These are just numbers. You can look them up. Mu static is always bigger. So, for example, let's just say you look something up and you find static friction is 0.4 and kinetic friction is 0.3. Generally, these numbers are less than 1. I have to look up what they can kind of reach. But coefficients of friction are generally less than 1. I don't know if that's a rule. I think that's probably... I don't know if that's a rule. All right. Why? And I'm going to give you all the explanation that you can explain to anyone. That, like, even elementary school. Use your hands. So remember that friction is because there's bumpy things rubbing up against each other. Oh, look, my fingers are kind of bumpy. You know, when you put your fingers together, you got bumps. When they're not moving, your fingers can kind of nestle into each other. All the little, like, bumps can nestle into each other and kind of get all cozy, and they get kind of stuck. When you start moving, they can glide over each other, and that's why the kinetic coefficient of friction is less. When you're moving, they can glide over each other. When you stop, they kind of nestle into each other. That's the explanation I give for this. You can, like, everyone can you can experience it, be like, oh yeah, they glide. So yeah, once you get an object moving, getting it moving is the hardest part because they nestle into each other. All the nooks and crannies get all kind of nestled. So to kind of draw a picture of that. And static friction, here's my things, and they kind of get nestled. But when they're moving, they kind of just skate over each other. All right? Microscopic level explanation. There you go. Fantastic. When a tire is rolling without slipping, what type of friction is responsible for the wheel getting pushed forward? I know. Here's a wheel. It's rolling clockwise. What type of friction is responsible for the wheel getting pushed forward? Is it static or is it kinetic? Think about the interface of the tire with the wheel. Or sorry, the tire with the ground. What is the definition of static friction? What is the definition of kinetic friction? When do they occur?
See, I've got that down.
All right, y'all got 5 more seconds. 5, 4, 3, 2, 1. All right. The key phrase here is without slipping. Without slipping. So, static friction is when your 2 points are stationary with respect to each other. Kinetic friction means they're sliding. When your wheel makes contact with the ground, so this little spot right here, if you're not slipping, your wheel is stationary with respect to the ground. The point of contact, think of like your shoe. When I push off the ground, it's static friction that makes you walk. When you walk, it's static friction. You push on the ground, your foot is stationary with respect to the ground, and it moves the rest of your body forward. So, yeah, the interesting thing here, it is static friction that makes the wheel spin forward, unless it's slipping, unless that wheel is slipping in space, at which point you don't get as much grip, and it happens. But yeah, you can kind of experience this for yourself. When you move forward, you push backwards, and your foot literally pushes back on the ground, and the ground pushes you forward. How does a wheel work? For every force, there's an equal and opposite force. So if friction pushes backwards, guess what the ground's going to do to it? It pushes the whole thing forwards. For every force, there's an equal and opposite. This is how you walk. Friction, obviously, you all know you need friction to walk. If you walk on ice, it slides in place. When you walk, you push backwards. Friction pushes you forwards. Actually, I drew this picture wrong. Friction pushes pushes forwards. The tire pushes backwards on the ground, and the ground pushes the tire forwards. There you go. There is an applied force. The tire literally is applying a force to the ground, just like literally do it with your shoe. When you walk, you are pushing physically backwards. To walk, you do not push forwards. You push backwards, and the ground pushes you forwards. Newton's third law, every force is an equal and opposite. All right. So here's some examples. Like I told you all, every single interaction between two materials has a different coefficient of friction. Rubber on dry concrete, rubber on wet concrete, wood on wood, metal on wood, steel on steel, steel on oiled steel, Teflon on steel. Like literally any two objects you think about have a different coefficient of friction when they interact with each other. And you have static and you have kinetic, and in every single case, static is always bigger. Oh, is there one that's equal? Teflon on steel. There's probably some decimal places that aren't listed. There's some decimal places, I'm sure. It is more than 0.04. It's 0.04 number. They round it. All right. Let's see here. You do not need to know these numbers. You do not need to know any of these numbers. I will either give you the coefficient of friction, or I will ask you to calculate it. So, all right. Case in point. Try it out. Draw a free body diagram. Sum of forces in the x equals max. Sum of forces in the y equals may.
But I think in India, really like this.
Oh yeah. I like what you got. Look at that. This is all for Draw a free body diagram. Sum of the forces in the x equals max. Sum of the forces in y equals may. Let's do the math. And the good news, y'all, after this, I only want to go over inclined planes, and then that's kind of it for today. So we've just been practicing these problems. We introduced friction, and now I'll introduce inclined planes, and that'll be all that we kind of want to cover. Thursday we'll talk about circular motion. And then we'll do a lab with inclined planes. They're puzzles. Not fun ones. Not fun ones. What do you mean? You ever played with blocks as a kid? This is basically playing with blocks. This is not playing. Yeah. What in blocks? What in grade? You're saying things. Well, then you know how. What a blessing that you get to experience this additional level of fun. Yeah. Now you all play with blocks. We should talk about. Anytime you all see those rocks hanging on each other, you can talk about. See, static fluid is 0. Now we actually never learned about fluid in physics. Like it's obviously a physics concept in my entire in all my classes. None of them lie about. So unfortunately, that's an area that I don't know as much as I should. Pascal. Yeah. There's PV equals equals area. Hydraulics is super interesting. I would do the second layer. No. Fluid is not to find the force. You don't have to calculate. You have to calculate anything. No, then you're not working with fluid. Yeah. You gotta make it airtight. You're working with forces. Water on the boat. You just gotta get the water out. And then apply that force to overcome force of friction. This problem on water. It's the same thing. Alright, so free body diagram. For once, our picture will look like our thing. Look, it's a crate. It actually looks like a crate. For once, they look the same. Crazy. You have a force of gravity. You have a normal force. Which way do you all want to push this box? It doesn't specify. Pick a direction. Left or right? Right it is. How does my... And then if I try pushing it to the right, what's fighting it? Friction. How does the force of friction compare? Does my box move? In part A. No. So how does this arrow size compare to the FA? They are the same size because it's not moving, and if it's not moving, it's not accelerating. There you go. What a beautiful picture. So what maximum force? What's the maximum amount you can push with before it starts moving? Givens, mass is 120 kilograms. Mu static is 0.5. Step 2, we are solving for FA max. So when we do report a static coefficient, it's based on the max. To kind of clarify. You can push any object up to that point. The static coefficient is calculated at the point at which it stops. At the point at which it starts moving. That's how you calculate static coefficient. Step 3, y'all, it's all free body, it's always the same. MAX equals sum of forces in X. MAY equals sum of forces in Y. F net equals MA. F net equals sum of forces. They equal each other. Let me do it again. Yeah, go do the answer. Let me put the answer up here, because that's always a natural question. What is the answer? Am I doing it right? There's the answer. I Yeah, so that is that's gonna result in static motion. But that's kind of the way to static motion stuff is at the point of pressure. Just like you technically did do it. You did do it. What's the acceleration in the y direction? This minus this. Right? And the x direction. This plus this. If it works, it's because we're following the right line. This is more. All right, y'all, how we doing? So in part B, we find the yes. Once you start pushing, you have to your friction force no longer inside. You have to use it All right, so step 4, you will use both of these equations, whether you realize it or not. You are using them. My acceleration in the x is 0. So it's 0 equals, what are my forces in the x? Fa max plus negative Ff. In the y direction, what are my forces? Or what's my acceleration? Also 0. You end up using both of these equations. So I'm going to copy and paste this over because I'm running out of precious room. Boom. Go away. You have to use both of these because you don't know what Fn... And you might have been able to realize this from the picture, and that's awesome. All the math does is express what's going on in the picture. If your picture is good, everything else is good. All right, so 0 equals Fa plus Ff. We could rearrange, negative Ff. You can rearrange this to get that Fa equals mu Fn. Force of friction is mu Fn. So if I can find Fn, I can solve this problem. The one over here, we then use this equation. 0 equals Fn plus negative Fg. Rearrange this. Fn equals mg. Boom. Now you got Fn. Put it there. You know mu. Put it there. And there you go. Set up the equations. So Fn equals Fg. Plug that in. Multiply by mu. There you go. All right. For part B, I'm not going to actually do part B, but we will. I'll just talk about it briefly. For part B, it says find the acceleration once it starts moving. What kind of friction do we have when you start moving? Static or kinetic? kinetic. So once it starts moving, it's the same picture. For part B, it's the exact same picture. Your FA is what you just calculated. But your friction is going to be kinetic friction. It's the same setup, and I give you the coefficient of kinetic friction to do step 1. Okay? So I leave that one for you all to kind of do. I want to get to inclined planes, and that be the last thing that you kind of cover. But yeah, part B, you're calculating A. A is not 0. Once it starts moving, by definition, if you start moving, you accelerate. You went from nothing to something. That is the definition of acceleration. That is based on the definition. All right. Inclined planes. It's good for you. It's good for your health. Inclined planes are good for you all. All right. Draw a free body diagram for the following situation. Before I even show you all a picture, I want you all to try it. All right. I got a box on an inclined plane. Draw a free body diagram for the box in the following situation. There is friction. And you can decide whether or not the box slides or not. That's up to you. You all can do this. Don't look at the next slide. It gives too much away. Try it for yourself. Yes, I'm going to show you the answer, but it will make more sense if you try it first. Because you can do this. Every single one of you can draw this free body diagram. There's nothing new to drawing this free body diagram. All I have to teach you with inclined planes is how to tilt your head. You're going to see what I mean. An inclined plane looks like a flat surface if you tilt your head. You were going to do flat surfaces. That's my encouragement to y'all. If you can turn your head slightly, you can do inclined plane problems. All right. So y'all tell me what forces are acting on this. Gravity. Which way does gravity always point? Down. FG points down. All right, what else is acting on it? Friction. Which way will this box want to slide? It's going to want to slide down the hill. Friction is always opposite to the direction of motion. This block wants to go down the hill. Friction is opposite. There's one more force I need. Normal. I have two surfaces touching. Normal force always points away from the surface. Normal force always points away from the surface. If two things touch, if I lean against the wall pushes against me. This box is effectively leaning on a wall. Okay. So here's what I'm going to encourage you all. And you're going to see this in the next slide. I don't know if I can do it with this. I might have to be creative. Yeah. All right. Here's my challenge to you all. This problem may look gross, but through the power of pasting it as a picture, it's just this. It's just that. It's a flat problem where gravity is at a slight angle. That's my thing I'm going to be trying to communicate to you all. So guess what we're going to do with gravity so we can actually use it? What do we have to do in any problem to do net forces? We have to break them into components. So the only challenge to this problem is realizing you have to break gravity into the part that points down the hill and this part. If you rotate your head, it can be easy to see that. Just tilt your head and it's the same. Now we realize, oh, gravity is no longer lined up with x and y, break it into components. Everything else is lined up. So, case in point, now we have better pictures than the ones I drew here. That's all this is showing you all. That's all I'm showing you all here. It's the same thing. We're just going to make x and y go down the inclined plane because you can do that. Just take this picture and through the power of rotating it, ta-da! They're the same. If you tilt your head, an inclined plane is a flat plane. So you can use everything I've taught you up to this point to solve this problem. The only new thing here is you got to break gravity into its x and y. That's the only new thing. Gravity will have some component that points to the right. We'll call that FGX. And gravity is going to have some component that points in the y, and that points down. That is it. And then it's sum of the forces in the x equals MAX. Sum of the forces in the y equals MAY. Yeah.
Why is it that the normal force is not like opposite to gravity?
Yeah, so that's a great question. Every question I've given you up until this point, normal force was this opposite direction of gravity. The reason that is not the case here is because the technical definition for normal force is always, perpendicular. It's always away from the surface. Normal force is always away from the surface. That's the better definition to follow. Yeah. So that's the other thing you have to realize here. It's not always opposite to gravity. Angle. It's one of those two options. And I'm going to teach you all how to find this without having to do geometry. I'm going to teach you all how I do this, which is I do not do a bunch of trigonometry relationships and geometry relationships because I always forget. I always have to logic through that again. I'm going to teach you all kind of my logical way of thinking through this. And then, yes, I will show you how to kind of do this. So, here's how I recommend doing these problems. What happens to this part of gravity, FGY, the part that's going into the board? As this becomes flat, does the part going into the inclined plane get bigger or smaller? As this inclined plane becomes flat, imagine this angle goes to 0. Go to a situation that you're really comfortable with, 0. Does the part that goes into the surface get bigger or smaller? Does the box push into the surface more or less as it gets flatter? Does it push into the surface more or less as it gets flatter? As theta goes to 0, does FGY go up or go down? Does the component of that go up or go down?
If the x component is increasing, then the y
And the extreme situation is literally all in. Or you can think of it vice versa. What happens to the x component? The y component will do the opposite. What do y'all think? So think about in the extreme situation, all right, y'all got 5 more seconds. Enough time for me to get back to my computer. 5, 4, 3, 2, 1. All right. So pick the extreme example. It's flat. It's flat. Gravity is pointed all down. So as this thing gets flatter, FGY gets bigger. FGX gets smaller. Why is this useful? Why is this useful? Here's why. Let me pick that answer. And it's okay if you this is kind of a shortcut way to do this. You can also just kind of memorize things. So I'm going to take this picture. As theta gets, as the angle goes to 0, so which is the biggest? Which is the biggest out of the following options? Is sine of 0 the biggest? Is cosine of 0 the biggest? There's only 2 options. Y'all just told me as it gets flatter that the y component gets bigger. So basically I have to choose, is it going to be sine or cosine? Which one gets bigger as angle goes to 0? Which one's the bigger value? Sine of 0 or cosine of 0? You all got 20 seconds for this. All right, 5, 4. Oh, refresh it. All right, 3, 2, 1. All right, this is just a math question. It's cosine of 0, if you didn't know. There you go. Those are the values. So, put these 2 pieces of information together. If I want to get FGY, basically my question is, am I going to multiply FG by cosine or sine of the angle? Well, we just said the y component's going to get bigger. So I need to pick the one that gets bigger. Which one gets bigger? Cosine gets bigger. As the angle gets smaller, cosine gets bigger. And we know that the y component gets bigger. This is how I think through this. You can do the opposite. Do the x component. Do the part that slides down the hill. As my thing gets flatter, it's not going to be pulled down the hill as much. Which one makes that happen? Sine. Long story short, that's the angle. If you set that up, cosine is the adjacent, sine is the opposite. Now, that's how I logic through it. I just think about, it's called boundary conditions. Boundary conditions. Take the opposite case. If I make that angle 90 degrees straight up, which one wins? The x component. Which one wins when this thing is literally straight up and down? Just rotate the picture. Which one wins? The x component. Yeah, depending on how you frame it. Now, you can do geometry to figure this out. There's some geometry tricks, and I always have to kind of think through it. It always hurts my brain to do the geometry for this. Here's a nice picture of it.
Yep, there it is.
There's a nice picture that shows you why geometrically this is the case. If this angle is theta, this angle is 90 minus theta. This is a right angle, therefore that's theta. There's 2 ways. I always forget this, though. I'm glad I have the slide, because it would have taken me a minute to remember this. I just think about if it's flat, which wins. If it's straight up and down, which wins. I know it's going to be cosine or sine. I choose it based on that. Or you can write this on your note card. I really don't care that much. You got a note card. Oh, speaking of which, I'll bring 5x8 note cards on Thursday so you all can start making your note cards. You don't have to buy one. I will bring them. But yeah, this exists, and all this tells you, great, there's the x and y. We just talked through that. The normal force will equal the force of gravity into the plane, so you can use that to find this. But this is a skill that you all should be able to do. So I give you all the note card. You do have the option of writing this down. But it is very important for you all to be able to kind of rotate your frames of reference and be able to determining how an angle I give you corresponds to a different angle. Being able to say that this angle is a very important skill that will translate outside this class. You will encounter problems where they give you an angle and then you have to figure out a different angle based on that. I highly recommend you all to remember certain trig things like that these angles are the same, these angles are the same. Remember similar triangles, share the stuff you learned in 9th grade geometry in high school whenever you took geometry. I use those all the time in my physics undergrad. These little like trig relationships, realizing if this angle is this angle is this, you all need to know that. I can guarantee you all need to know that in the future. Being able to take an angle and find a different angle from it. And these little tricks, realizing similar triangles or boundary conditions. If this changes, how does this change? That's how I do it. That's easier for me. My memorization stinks. So if I can just logic through if this, then this, I like that. All right, last problem for today, y'all. This is it. All right. I'll draw the picture for y'all. There it is. See if y'all can get this. I will kind of give, as I did with every problem, I'll give checkpoints here and there of if you haven't gotten the next step, here it is. But also cross over. But this is it. This is the last problem that we're going to work on today. The last problem I'm going to work through. We're here to help you. And then on Thursday, we're going to do a lab with this. And we'll talk about circular motion, and that will be it before the test. So we're doing really good time-wise. I've taught you all 95% of what you need for the test as of today. There's only one last little tiny little bit, which is centripetal force.
Professor James.
Yeah.
Sorry.
What's the question?
That's me.
Yeah, Tuesday will literally just be review.
Okay, yeah. Let me actually tell you when that is. Great question. Tuesday next week is a review day. Tuesday next week, I will not be taking attendance, and I will not be doing clicker questions that are worth a grade. Next Tuesday is us just practicing everything. So a week from today is all review. A week from today is review. So I'll go through problems. I'll go through, here's what you need to know. I'll go over like really good problems that I think are important to know. All that kind of jazz. Concepts that are important to know. If you decide to be here, great. If you decide to not be here, you're not going to be penalized. There's no attendance next Tuesday. There's no clicker questions next Tuesday. So that is kind of an optional day. That is just basically my office hours. I'll be guiding us through problems as well. It's just going to be, hey, here's some stuff. Here's some things to think about. Here's some important ideas. Oh, last thing. There is a test review. So if you're like, man, I want to start preparing now, and you're like, what are the important things to know? If you go to files, I have all the test reviews from last year. I already posted them here. They're the exact same ones I did last year. Now, granted, this was for a 50-minute class. So we are going to be able to do way more than I was able to do in this review. But look, it's a summary. It's a nice summary slide. I'm actually not going to go through this again. I'm not going to make this again. I'll actually talk through this next Tuesday, but it's a summary of what you need to know. Oh, nice, right? Look, it's even got pictures. Yeah, there you go. So that's there. Look, test 2 review is also there. Test 2 review, if you want to see that, also exists. Final review also exists. The beauty of teaching a class before is I get to reuse things. So I will. Yeah. A week from this Thursday. Yep. And this class. Yep. Test is during normal class times, Thursday, 8 to 10:50. If you show up late, you will just lose however many minutes that you show up late. So don't show up late. I will not give you more time if you're late. Make sure you get here at 8 o'clock so you get as much time as possible. I will start handing out the tests right at 8 o'clock. to give everyone as much time as possible. You get the full 2 hours of it. It's an excessive amount of time for the test we're designing, but that's a good thing. Time is not a concern for me. If I could give every class that like an excessive amount of time, I would. But that's one of the benefits of this. You'll get saved. It'll be similar. So my other class is an hour and 20 minutes. So I'm not. So in their case, instead of having 3 for response, they get 2. They get 2 for response. Otherwise, might get some differences. No idea. Probably not. Probably not. For the sake of it, so one of my responsibilities is scheduling TAs, and that's been a learning curve. And so that's where it's like, probably not. You get full 2 hour 50 minutes, but I'm designing the test for like an hour. As in like, yeah. If you had that much time, an hour and 40 hour 50 minutes, it's just completed. Everything extra is if you want to use it, go for it. There's no shame, there's nothing wrong with that. If I could do every class and every test that way, I would. But that's one of the benefits of this class. There's so much class time.
He expects you to have like bumps out.
They get an hour 20, and their test instead of if you read the responses, they get 2 responses. So the way to work is you will have to choose the grader, which will be me and the TA. You will only look at the third one to see if it's perfect. If it's perfect, then we'll take it. Otherwise, we're not going to grade through it. We'll take it for grade.
So you can
do all 3, but we will literally just look at the one you have to mark 2. If you don't mark 2, I'll just grade the first 2. And then we will look at the third. If it's perfect, sure. Then we'll replace the other one that's not perfect. But otherwise, we're not going to go through the full time of grading all 3. Just because that'll add extra 50% of time. But 20 to 25. So it'll be 20 to 25 multiple choice. And then the third one will be 2 out of 3, and they'll have 2 parts. And those are probably that would be like 2 parts. So 2 parts. So the expectation is 20 minutes for every response, and then roughly 3 minutes or so for on average, some of the goals go close to like 30 seconds. Some of them might be a little bit longer. And that's, if you know what you're doing. But that's kind of what I plan for.
Even if we had to memorize that, like,
Nope.
we just write it down.
Nope, it's scans around.
Like, ask them about
There is no FA in this case. This is the force pulling it down. Yes. So in this case, FA is FA we generally say for someone like this or something. So yeah. Yep. All right. To give you all a checkpoint on, and I'm gonna write up a whole announcement about the test that'll have all the details. The only thing you need to bring to the test is your 5x8 note card, yourself, a pencil, and a calculator. I do not care what calculator you bring as long as it's not your phone. I don't care calculators. As long as your calculator can only do math, I'm good with it. Phones can do more than math. I don't care if you use a graphing calculator. I don't care if you use a scientific calculator. I don't care if you use a 4 function, just a plus or minus. I don't recommend it. So you, pencil, note card, and a calculator. Also, some ID with your name on it, though I actually recognize most of y'all. I just need to know when you turn in your test that it's you. The biggest thing I have to avoid is someone else taking your test for you. But honestly, if you tried to pull that in this class, I'd be surprised. I recognize your own faces at this point. That'd be wild. If I saw someone, I'm like, I've never seen you before. Who are you? I would probably ask them more questions. Anywho, all right, for this problem, y'all, what's given? Mu, kinetic. That's kind of it. MAX. And here's the important thing, y'all. X is down the hill. Y is perpendicular to the hill. Remember, these problems, you have to tilt your head. Tilt your head. So MAX equals sum of forces in X. MAY equals sum of forces in Y. You do not need the mass for this problem. You do not need the mass for this problem. Yeah. FG times sine of that. And also you gotta be careful in the x direction. It's not just gravity. There's also that. So in the x direction, it's this plus negative this equals sum of the forces. Yeah, you were missing friction and so in your all's picture, you need gravity pointed down. You all need normal force pointed this way. You all need friction pointed this way. And then you have to break gravity into its x and y. You have to break gravity into the part that pulls it down the hill. And you have to break gravity into the part that goes into it. And then you sum the forces in the x equal to max. You sum the forces in the y and equals may. Hey, what is my acceleration in the y direction? In this direction, what's my acceleration? 0. My box is not leaving the surface. Tilt your head. Is your box flying up off the surface or down into the surface? No. AY is 0. AY is 0. Y here is not up and down unless you tilt your head. Then it's up and down. Remember, the key to doing these is turning your head sideways and realizing it's a flat surface. That's the key. Step 2, we're not solving for A, we're solving for AX. And mass cancels out. You don't need mass to solve this problem. Set up the problem and you'll see it for yourself. Set it up. Set up these equations here. That is the key. You got this. I'm here for you if you don't have it. You know the acceleration of the y is 0, so you're solving for No, you need a bigger equation. Yeah, step 2 is just saying what's the reaction. Will do that for us. And then I'm going to put my...
Yeah, I'll let you.
Stop bothering me. I'm busy. It's not bothering. If y'all heard me say it's not bothering me, it's these notifications. You all keep bothering me. Goodness. Let's go back and. All right. So again, these problems, can you set up the net force equations? That's all. That's always the skill. So MAX equals FGX plus MAY. Stick around if you're not sure what to do. If you leave, I'm assuming you know what you're doing. If you don't, that's on you. I'm not. So the GX is what? Yes, that's it. So basically, we're taking this, splitting it into X.
Yeah, I think it's ignore.
As this angle gets smaller, this swings towards. So as this kind of swings down, so this is in degrees.
Yeah, use gravity. And then solve problems.
You need math for the force and applying math.
What is that?
Sure, let's see.
So this, so gravity goes down. So you either going to use or this. Either way, to get the two.
Apple, what are you doing?
Oh, yeah.
Yeah, but I mean, this should.
It's
right?
That's so bad.
They don't do it.
Like ours was
Surface code. That's how this. That's the deal. I'm the Apple show. I've seen how many app. I feel like they left a button on it or something.
Oh, yeah, no, that's the second.
You gotta pay extra for the button. Yeah.
It's like $50 extra.
Yep, classic.
Yeah.
I mean, these things are also expensive, so look, we're not gonna. So yeah, I don't really have to draw any more.
just watch live.
And so, okay, this triangle doesn't quite right still.
Yeah, so what we're doing is
Guys, I'm gonna you don't need math.
you made a run league.
So this is it. So then the big thing you're working on before, it ends up and the way I explain that, as this gets flatter, this swings this way. So think about it, as this gets flatter, the force force of gravity more lines up there. Except for just, take the extreme. You have something literally on a flat surface. FG is straight down. Which means that this is more. And then, you stop sliding. As it gets flatter, it stops. This is the force that causes it. No. So my pictures here are
The guys away that
to find the acceleration.
like the force is like last I'm not sure. Instead of using the force, we use what it means. And it has mass.
It's going to be that.
Yep. So alternatively, you can do this. Or you can do this on the sine of 10. Because this is.
Yeah.
There's always two ways to draw this triangle.
That makes a lot of sense.
I said the x component. The x component. So the good news is, if you want to you get 75%. Right? Not forgetting it right is, and even at the end, once I got it, I agreed. Oh yeah. So you have to every single one wrong. Anything extra is
No, I am. No.
you spend as many as possible. So remember on this slide, FGX is that. It's the sine of FGX. Look at the picture right here. This is the angle. Yeah. This is FGX. This is FGY. It's just a triangle. It's a vector. Yeah. So to get the x component, to get this component, it's this times cosine of the angle.
Yeah.
To get this, it's this times the sine of the angle.
Yeah.
Yep.
And that's all we have to find. That's it.
Then you have to plug them in and do some math. At the end of the day, we're solving for this. So we put the x component in there, we put the y component in there, and then you solve for ax. Yeah. I appreciate how many of you are sticking around. And
I don't have
yeah, it's not just like once you do it, all these force problems all break down into this. That is the bread and butter of these problems. So after you do a few of these, that skill set will translate to all the problems. So it is using the same skill set, even though the context looks different. I don't expect everything to. No. You're fine. You're allowed to be done. That makes sense. I was just saying, it's okay. Like, I don't expect you all at the end of class to understand everything we did. I expect this to give you some foundation. So when you then, it's going to process in the background. And then when you look at it later, bit more will make sense. You still do have to spend some time outside of this time. And how much, just depends on how much makes sense at the end of class. Yeah. And that's. The benefit, though, is I'm just able to do more. I'm able to give you a better foundation leading into you working on your own lecture. I just work through all these things, and they don't understand. Like the percentage that I expect you all to come out of class with is a high, not grade wise, but literally like understanding is higher in this than my life.
Should we study the quizzes as well?
Yeah. Those quizzes are basically
They're like on
a mini version of it. They're not the exact same problems, and it's not even like a guarantee that I'm going to pull any of those problems. But they are a representative sample of what you can expect from a test, kind of thing. Difficulty and content wise.
And they're still up if I want to read.
Yeah. Oh yeah. And I post the solutions.
Oh yeah.
Actually, I need to do that
Like worked out.
for the quiz problems. Just for the quiz problems. I purpose.
Is it like a question goal, or is it like everybody gets a question?
I'll leave that as a mystery. I'll leave that as a mystery. I don't want to give too much away. I will say each test has a similar level of difficulty. I can tell you that. But I will leave there is different versions, but I won't specify how I make the different versions because that's my secret.
Labs are
Yeah, that's right. Yeah, so basically you're gonna take this one. It's really helpful for people. No, you're good. Exactly, because they're going to be equal to each other in this situation. Yeah, there you go. Got a couple steps, but all of these sports problems all boil down to the Yep. Once you see it enough times, it'll be obvious. Once you see it enough times, it's going to be obvious. But getting there is tricky. What's up? Huh?
I just had my phone in my backpack.
Yeah, it's healthy, right? Now, what'd y'all think? Smooth?